So hi everybody, my name is Alex Hanmore. I'm the manager of concrete technologies at Biota, and I'm here to present to you all today Digital Aggregate, which is our tool for analyzing concrete aggregate physical properties using computer vision. So what I want to go over during this presentation is digital aggregate. So what is it? How is it used? Then I want to talk a little bit about size and shape parameters of aggregates, how it's applied using digital aggregate through a case study, and then talk about how this can be used to reduce GHG in concrete production. So what is digital aggregate? So digital aggregate uses computer vision to generate highly accurate aggregate morphological data to enable opportunities for quality control and optimization. So is it a tool that allows for rapid testing that provides much more information than you would typically see through regular aggregate testing? So what does it look like? So first, we would have a sample of our aggregate. We would look to lay it out into a nice flat pad, and then we would use any phone, camera, anything to capture images of that aggregate itself. And then as long as we have a reference scale in the picture, we can use that to characterize this aggregate. So the reason we need to include a reference scale is because some people might be taking pictures from higher, lower. They might use one phone versus another, one camera versus another. We wanted this to be universal so that anyone could use any image capturing device and learn more about their aggregate properties. So you take a picture of your aggregate. We would then take that, agitate it 4 times, taking a picture for each agitation to create 5 images. The process itself takes about 3 minutes. So we found it important to include agitation in this because otherwise all you'd get is good surface area, but what you want is true 3D imaging of your aggregates. So you could think of it as trying to take a picture of an iceberg from top down. Really, you just get the surface area, you miss that 3rd dimension. So this data is then sent to the digital aggregate algorithm where it is analyzed and then produces insights into shape and size parameters of your material. So I just wanted to present this through a case study where we looked at 4 different types of aggregates. We wanted to have a wide range of color, shape, size, angularity versus roundness. We looked at 4, one on the left, which we just called the cheetah print aggregate, so high, multicolor, even difficult with the eye to see where one particle starts and the other begins. The other LC, which was the local in-house aggregate that we use in Cape Breton, Nova Scotia. The other one, which we just called the panther aggregate, which is one single color, flat tone, and the other, which was a smooth river stone. So as mentioned, we try to have a big, diverse group of shape, size, color. So what the digital aggregate tool actually does is it would take these images, it would segment each particle, it'll track them, identify them, and then provide information around shape and size parameters. So each of these samples would have been imaged 5 times to get 160 total images just for these sets alone. For this case study itself, these aggregates were split into 8 different samples to give you an idea of how this will change from sample to sample, from batch to batch, through all the tests that we looked at. So first, I just want to talk about the size parameter analysis. So I think first to show that it's worth exploring the sieve analysis itself and where there might be some gaps in this test. So as I mentioned, we took one of these samples and split it into 8 and then ran the gradation on all 8 samples. And there was still a pretty wide range of variability. These were supposed to be seen as the same sample. Whether the error occurred in the splitting, the testing, the data collection, what have you, there was a pretty big spread in this testing. So if you were to look at this aggregate itself and put it through the ASTM C33 bounds for what's acceptable for a number 67 aggregate, you would see that some of it actually fell outside of the limits. The majority of the testing would have been okay, but 1 or 2 of them probably would have failed your test. Though if you took an average of this data, it actually does fall within the bounds. So there would be no concern if you average all of this, if you were to sieve all of your samples as opposed to just the single 5 kg units. But most people don't do that due to time constraints or whatever else. But we find that by using a tool like digital aggregate, you could image all of that aggregate and get a true representation as opposed to just a segmented 5 kg sample. Now, just to show that the equivalence of this digital versus true sieving, we have what we call the sieve equivalence, where we wanted to compare just one sample from a set and the average of that same set. You can probably see, get my cursor up there. No, maybe not. So there should be just a light shaded bound. Maybe it doesn't come up too well with this color scheme, but that is the acceptable range and bias tolerance from the ASTM C136. And we showed that whether you did the digital sieve or the standard sieve, they did fall within the same bounds of acceptable error. Oh, there we go. There, yeah, I just wasn't sure if we could really see it is a pretty tight range, so maybe you can't really see that too well. So there was no problem segmenting the cheetah, which was the multicolored stone. We did look at the sum squared error as well, which gives you the idea of if you take these points, subtract them, square, and sum that average, what would it look like in terms of error? And all of them are less than 1%, which is seen as a very tight and acceptable error in this case. Same as the LC aggregate, no issues, very repeatable when it comes to digital versus traditional sieving. Again, very small error. When we looked at the Panther, which was a little bit of a smaller aggregate, there might have been a little bit of a discrepancy when it comes to the upper bound of that analysis. But we did find that with more imaging and then retraining of a model, you start to lose all of those little bits of error. And then lastly, when we look at the Riverstone, it was also comparable. Same doing digital sieve versus traditional. And here's just a note about the error itself. So we did have some that were a little bit in the higher range, like a 2% error in this one, 2 here. But if you do take the average of all of your errors, as if you were to image all of these samples, it was repeatable and would give you the same predicted results. Next, I think I want to talk about the data repeatability. So if we did look at the same sample, image it, and then image it again, would you get the same results? I also thought it was important to assess if we added more moisture in one case. So all of the sieve testing was done in dry aggregate. However, if you wanted to speed up that process, could you image it with wet aggregate instead? And we found that we could still segment the images all the same, as it is based off of shape and size parameters, not color or moisture content. And whether we compare the dry aggregate to the traditional sieve or the wet, you do get the same results. Again, with very minimal error. So if we were to look at the comparison between these two cases, standard sieve testing, you do have to run through the process of splitting your sample, drying your aggregate, conducting your test, and then your data analysis. Whereas the digital or sieve equivalent, you just have to take your photos, upload it to the software, and then it's finished. So because it does speed up the process, you can take more samples and get better representation of your true data. I think it's also important to think of what does sieve analysis truly tell us. To help answer this question, I did take these samples and run them through just a series of measurements with calipers. So the length would be the longest side of an aggregate, width being the longest perpendicular, and then thickness being the shortest dimension. This example was done from a 3/8 retained sieve, or 9.375 mil, which is what that red line is here. And what I found was what you see is just, you can tell that the average of your smallest dimension is a little bit under the retained sieve size. So it does give you some good information, but you are missing information when it comes to your longer two sides. But if you know a lot more information about the shape of your aggregate itself, you can really get rid of that error that you might see otherwise. So brings me to the shape parameters. So there are some existing shape parameter tests out there right now. So whether it's flat and elongated testing or flakiness and elongation, those who have done those tests, you know they can be quite time consuming. You are taking the sample, you're splitting it, drying it. You pretty much run through the whole sieve process. You take one single fraction of that, and then you have to do a dimensional analysis. So if there is concerns with the sample being represented from the sieve, that same problem will cascade down to a flat and elongated testing as well. So with the digital aggregate, not only do you get the shape parameter, but you also, or size parameters, you also do get information about the shape. So we have many different parameters we can look at here, one of which is the circularity. So pretty much how close is the two dimensions you can see to a perfect circle. I think that the one that I would point out would be this red one here, which was the Riverstone. You can see that it would be seen as more elongated than the rest. So in this case, when it's less like a circle, the more the values decrease from 1, the more elongated or irregular you would see. Also, if we start to think of angularity of aggregate, there is some guidance through ACI, but a lot of it is a bit open for interpretation. So there can be a 1, 2, 3, 4, or 5-point scale on angularity of aggregate. But what happens if your aggregate is between two of those sizes? Does that number truly capture all of the aggregates in question, or is it just one or two that you looked at? We figured that it would be better to assess this through a continuous curve of data, because that can give you the true angularity of your material itself. So the example parameter we looked at here is the one that we called compactness. So the values closest to 1 indicate that the shapes are compact and smooth. However, if you have high compactness, it would talk more about irregularity, elongated, or indented shapes, which we could correlate to angularity of material. Another one that I wanted to highlight was what we'd call roughness. So I can explain a little bit more about what this one looks like on the next slide, but again, if we think of these rocks that we had in question, the riverstone, the smoothest rock, we would see that as having less roughness than the rest. The way we decided to calculate that was if you take a given particle, you have what we call the convex hull, which is the outer perimeter of the aggregate itself. You'd compare that to the true particle area, and the difference between the two would be what we deemed the roughness of this material. So just trying to put an actual value, a continuous curve of a roughness measurement for aggregates. So we do have many different shape and size parameters that we can review here, but I think just to keep on theme of this session, I did want to talk about how a tool like this could be used to reduce the GHG of concrete. So if we do think of the design paste using concrete, I mean the cement being the most carbon intensive piece of concrete itself, the idea to reduce the GHG would be to reduce the cement or to try to use an optimized amount of paste for a given system. When balancing that in your design, you do have to consider things like durability, the hardened and fresh property states, and then sustainability. But information about aggregates is really helpful for determining that workability parameter. You need to know how much paste is required to get a certain amount of lubrication or fluidity in a mix. And if you know more about your aggregate properties, you can better determine how much paste is needed for that fresh state. Another spot would be in particle packing models. So definitely not an expert in this space, and I know we have some more people talking about this one today. So I just did want to touch on, usually they're broken down into either continuous or discrete models. Continuous, assuming that they are all spherical particles, your aggregates, whereas discrete models, you need more characterization data, which is something we could provide easily through imaging, which could provide that information without all the necessary testing. It could also be done more rapidly and more frequently to provide that information. Another place where this could fit in is in AI optimization models. So you're seeing a lot more of these come to market where they're optimizing for things, well, whatever you want really, but something that could be optimized for is the GHG. And these models are really only as good as the data that goes into them. So right now, you're provided information of all the materials themselves, and when it comes to the information from aggregate, you'd probably see things like gradation, density, absorption, but we could, through our tool, also provide size and shape parameters for the aggregates themselves. Another space where this could be useful is in RCA. I think the jury's still out on this one, whether it actually improves GHG in concrete, but we are still wanting to use the recycled material where we can. So it is difficult to use today due to different shape, size parameters, also the variability in water demand, which is usually a function of the shape, size, and then the ratio of aggregate to paste in a given aggregate. So a tool like this could be trained to isolate cement paste and aggregate fraction in RCA to give you a true idea of water demand requirements and how that would fluctuate. Also, this could be used to assist the implementation of other green technologies. So many green technologies are looking to reduce cement. So usually they put something new in, take cement out, but to maintain yield, you have to fill that space with aggregate. So a better understanding of your aggregate properties would allow you to reproportion that mix to get the appropriate fresh and hardened state. And lastly, this isn't from any real data, it's just an example plot, but through the normal distribution of strength, by knowing more about your materials, you could tighten up your standard deviation, so having more QC, more information, and in doing so, the zone of failure, so the last, say, 5%, the tail end of that distribution curve could be brought up further, which would allow a bit more room for some reduction in cement paste as required. So, in conclusion, digital aggregate is a computer vision technology that analyzes aggregate properties. It offers size and shape parameters that are otherwise challenging to obtain in practice. This technology can be used as a more time-efficient method when compared to traditional practices, and it can also assist in the optimization of concrete mixes to reduce GHG in concrete. So, thank you all very much for your time.